Alrighty, guys. So as you can see, we are actually now getting into how to solve oblique triangles. So in chapter one, again, we studied how to solve right triangles. We looked at the different trigonometric functions, the Pythagorean theorem, SOHCAHTOA, and all of those different definitions to try and help us solve right triangles. So now let's get into how to solve oblique triangles. And basically, when we're talking about oblique triangles, we're basically saying you won't have any 90-degree angles in it. So just to remind you for the notation, the capital letters A, B, and C will be for angles. And then the small letters A, B, and C will be for the sides, which are opposite to those angles. So that notation will still stay the same. Now, when we're talking about solving oblique triangles, basically the idea is we should know three of the measurements. One of them should be a side, and then the other two measurements can be, two sides, two angles, one angle, or one side. So the idea is when we're trying to solve these oblique triangles, one of the measurements at least has to be a side, and then the other two measurements could be anything, two sides, two angles, one angle, one side. So this actually gets us into four different cases. So four different types of triangles that we can solve. So that means you would be given two angles and one side. And that could mean, we could be given two angles and, maybe any one of the sides, or we could be given the two angles and then the side, in between them. So that's kind of the difference between this notation. So two angles and one side, but just depending on the placement, is it angle, side, angle? So that would be something like this, or is it angle, angle, and then one of the sides here. The other one could be two sides and an angle opposite one of them. So let's say if these are the two sides that we are given, then one of the angles opposite them could be, you're given angle B or you're given angle C. So for these first two cases, we actually use the law of sines. So you can see for the first two cases, we will be working with law of sines, which is what we're doing in this section. For the other two cases, so that's cases 3 and 4, where you are given all three sides, which means you would be given the sides, and we would have to find the angles. That has to be solved by using law of cosines, or you could be given two sides and they're included angle. So that would mean, something like this, where you have the two sides and then the angle that's included between them. So that's the side, angle, side. So for those bottom two cases, we will be looking at those when we get into the next section, 3.2, using law of cosine. So let's look at law of sines and how they can help us solve these oblique triangles. So your law of sines, again, basically you have a triangle ABC with sides A, B, and C. So the law of sines is side A divided by sine of angle A, that is equal to side B divided by sine of angle B, equal to side C divided by sine of angle C. So remember, the small letters represent the sides and the capital letters represent the angles. That's why they have the sine function on them. Now you can obviously take a reciprocal of this law of sines, and you can actually also write it in this form over here. So any one of these two will work, just depending on what you're trying to solve and what information you are given. So just remember, either of those format of the law of sines will work. So let's take a look at our handout example over here. So this one, we are actually going with this first case where you have the AAS. So you're given two angles and any side. So again, you have your triangle over here. You can see we are given angle C, angle B, and then one of the sides. So angle C is the 102. Angle B is 29, and then you are given side B, which will obviously be across from angle B. So those are the three values that are given to you. So, again, guys, use the information that you already have. So everything is not given to you in this section. Now we know that 3 angles of a triangle will always add up to 180 degrees. So if we have 180 degrees as the total for the 3 angles, you're already given 2 of these angles at 29 degrees and 102. Go ahead and subtract that from 180, and whatever you're left behind with is going to be that missing angle, right? So if you're given 2 angles, finding the third one is as easy as that. Now, when you have to find the 2 missing sides, which will be side A and side C, this is where your law of sines is going to kick in. So at this point, if you look at the information given to us, we have angle B and we have side B, right? So you definitely want to use this fraction in there. Now, using this fraction, you can either find side A or you can find side C. It doesn't matter which direction you go in. So as you can see, they're actually going with side A first. So what they have done is they've taken this part of our formula from the law of sines. So you have A equals sine of A equals B divided by sine of B. Oh, why are you not writing? I swear this week technology has not been my friend. It's been acting really weird. So since we are finding side A, you want to get that letter A by itself, which means get rid of sine of A. So, of course, we go ahead and multiply both sides by sine of A, cancel it out from here. So you're just left with side A, and then on the right-hand side, you're left with B divided by sine B and then multiplied by sine of A. So that's basically where this guy comes from. And in that same way, you are getting the C equals B divided by sine B multiplied by sine C. Now, once you have rewritten that formula, plug in the numbers that you know. So side B, sine of B, we just found angle A to be 49. So sine of 49, throw that into your calculator. And you have your value for side A. Same thing with side C, plug in all the numbers that you know, and you can see that you get the value for side C. So there you end up getting your answers. And now we have all 3 angles and all 3 sides of our triangle. And so I thought this was kind of neat. Your textbook had this little trivia that the surveyors used the same idea of law of sines to calculate the height of Mount Everest. And this was back in 1850s, right? When we didn't have all these fancy instruments and technology, they used law of sines to calculate the height of Mount Everest. And you can see they came within 30 feet of the current accepted value, which is really impressive if you think about, just how different things were, back in 1850. So again, just a very simple rule, but you can see how that can help you solve, something like what is the height of Mount Everest, or, any kind of triangle or triangular shape that you might be trying to work with. So you've got a couple different examples over here. Here's another one where we are still doing case 1, but in this case, you are looking at angles, side angles. You're given the 2 angles and the side between them. So let's take a look at that. So this one here, is more like an application-based example. So this one is saying a pole tilts towards the sun at an angle, 8-degree angle from the vertical. So when they say 8-degree angle from the vertical, you can see if we were to create that 90-degree, if we were to create that 90-degree, from the vertical to the horizontal. So this would be our vertical, making our 90-degree over here. So from the vertical, they are saying this one here, as the pole tilts, it's making an 8-degree angle. So as you can see, it's marked in the little image. And they're saying it casts a 22-foot shadow, which is giving us the length of, the shadow over here. So we have, they're saying the angle of elevation from the tip of the shadow to the top of the pole is 43. So that's this angle right over here. They want to know basically how tall the pole is. So since we know that the pole is making this 8-degree angle from the vertical, well, we know this side here is going to be a 90-degree angle. So when we take that 90 degrees and add the 8 degrees, you are actually getting angle B as 98 degrees. So that will be this angle over here, comes out to be 98 degrees. We have angle A given to us as 43. And then we are given the shadow of the pole, which is 22 feet. So again, you can see angle, side, angle is what's given to us. And using that, they want us to find out, how tall the pole is. So that's going to be side A. So since you have two of the other angles, they're going ahead and using that same idea, 180 minus angles A and B, which ends up giving us 39 degrees. So angle C is going to be 39 degrees. And the reason why we're finding angle C is because we know side C. And since we know side C, we want to use that in our law of sines to help us find side A, which is going to be the height of the pole itself. So you can see that's the formula we go with. A divided by sine A equal to C divided by sine C. We're trying to find side A, so move that sign to the right-hand side, rewrite that formula. Side C is 22 feet. Angle C is 39. Angle A is 43 degrees. And you can see that will end up giving us an approximate height for the pole, 23.84 feet, just a little shy of 24 feet. So again, just using law of sines to try and figure out, how tall that pole is. And as you can imagine, guys, this can be used for any object that you're trying to find the height of, right? You need the length of its shadow. You need the angle of elevation. And like I said, we have better instruments now than they did back in 1850s. So you can find the angle of elevation with this instrument. So if you have that information, like they did with, do you have a vertical angle, 90 degrees, or is it tilting like this pole was? So what that tilt is, and based on that, we were able to approximate the height of the pole. You can kind of see the example we have here is related to finding this height of the tree. So just different ways that you can use this. So let's try and pick an example here from our textbook to solve one of these. Let's do number 9 here. So again, your instructions are use the law of sines to solve the triangle and round your answers to 2 decimal places. So we will work on number 9. Okay. Alrighty, so let's see for number 9. We are given 2 angles and 1 side. And if it helps, you can draw just a rough sketch of a triangle. Let's see, side angle A is 102, so that's definitely the largest angle. So let's see, angle A is 102.4 degrees. Angle C is 16.7. Opposite from angle A is going to be side A, and side A is 21.6. They didn't really tell us if this is in feet or inches or what, so looks like they're not really using unit of measurement with their calculation. Oh well. So remember, you're solving the entire triangle here. So that means we have to find the missing angle and we have to find the missing sides. So we need to find side B and we also need to find side C over here. So let's start with angle B. What do you think the measurement of angle B is going to be?
Is it 60.9?
Alrighty, let's see. Because it's still the same idea, right? Your three triangle angles in your triangle has to add up to 180 degrees. So you will take 180 degree minus the given angle. So that's 102.4 for angle A minus the 16.7 for angle C. And Lucy, you said 60.9
Yeah,
or 16?
60.
60. Very good. All righty, perfect. So you will end up with one decimal place in this case. So yeah, 60.9 degrees. So that will be this guy here. So, you know, obviously that was the easy part because we just had to do a little subtraction with angle B. Now we have to find the missing sides of angle B and, side B and side C. So I'm just going to go ahead and write our law of sines over here. So I write a little cursive C so it's easier to identify that that's the small letter C and then, you know, just a regular C for the capital C. So let's start by finding side B. So if we look at the given information, guys, we have side A and angle A. So to avoid a lot of rounding errors, you know, try and use the given side and the given angles as much as you can instead of the angles or sides that we come up with, because, you know, especially if you have a rounded answer, that can always affect, you know, when you calculate something new. So I'm going to try and stick with using A, you know, for finding both sides B and side C. So for finding side B, you know, of course, we'll be using this part of our formula over here, and you want to get side B by itself, which means we're actually going to move sine of B to the other side. So you will end up with A divided by sine of A, and then multiply this by sine of B, and that will help us calculate the side B. So let's see, side A is 21.6. And sine of angle A is 102.4. And then sine of B, we just calculated, was 60.9. So what do you think our side B comes out to be in this case? So let me see your answers. Again, I'd like you to share your answers with me in chat. And remember, they asked us to round this to 2 decimal places. Okay, let's see. Oh, Lucy, I just saw your question. You had asked me how many questions are on the final exam. I'll check. I'm not entirely sure. Let me go back and check on that one, okay? All right, Andrew, you've got 19.3. Lucy, you've got 19.32, 19.32 for Darren, and 19.32 Savannah. All righty. So, as an approximate answer, when I'm looking at my calculator, I have 19.324, you know, 27, and it keeps going. So rounding it to 2 decimal places will definitely bring us to 19.32. All righty, perfect. So that is going to be side B. So now that leaves us with side C. And for side C, you know, basically we'll be doing the same thing. So you will have C equals, and I'm still going to go back to A divided by sine of A, because remember, as I told you, try and use the given information more and not the information we came up with. So you want to try and avoid using side B if possible, since that's a rounded answer. So we've got, again, same thing, 21.6 over sine of 102.4. And then sine of angle C, and angle C was what, 16.7? So what do we end up with for side C as our measurement? And again, you're rounding to 2 decimal places. All right, Darren, I see your answer. Lucy, Savannah. All righty, 6.36. So again, the raw answer is 6.35524. So when we round it to 2 decimal places, the 5 in the third decimal place will make the 5 in the second decimal place go up. So yeah, very nice, guys. You will end up with 6.36 in this case. And basic rule of thumb, guys, that you should remember, I guess, from geometry over here is that the side from the longest angle will be the longest side. So just like in your right triangle, your 90 degree is always the largest angle. So the side opposite to it is the hypotenuse, which is the longest side of the triangle. That's still going to be true for an oblique triangle. So as you can see, angle A was the largest angle with 102.4. So side A is the longest side with 21.6. Angle B was the next angle in measurement. So side B is the second longest side. And angle C was the smallest angle. So of course, as you can see, your side C came out to be the smallest side of your triangle. So, that's a basic rule of thumb. You can always remember that your ratio between the angles will match the ratio between the sides. All righty, very nice. Did anybody have any questions on this example over here? All right, let's save this guy, clear him out, and then let's see. I think I had picked a application problem for us to work on. It may have been this one. All righty, so this one is talking about the bearing from Pine Knob Tower. So here's the Pine Knob Tower. Toward the Coal Station Tower is north 65 degrees east. Now remember, your bearings are always done in respect to the north-south line. Air navigation is a little bit different, but for the, on water, on land, we use the north and south line. So we're talking about from the north line, it's a 65 degrees going east. So you can see that's that 65-degree angle right over here. They're telling us the two towers are 30 kilometers apart. So that's the distance between the two towers. A fire spotted by rangers in each tower has a bearing north 80 degrees east. So again, using that north-south line, from the Pine Knob, you can see that's making that 80-degree angle again going east, and that's from Pine Knob. And then south 70 degrees east from Coal Station. So that's this angle over here. Again, using that north-south line, you're going 70 degrees east. So they basically want to know what is the distance of the fire from each tower. So that's what we're trying to find over here. So what I'm actually going to do is transfer this over to our notebook. Okay, let's see. Okay, so from the north-south line, we know this angle here is going to be 65 degrees. And we know this angle here is going to be 80 degrees. From this tower here, we know this angle is going to be 70 degrees. And the other thing we know is this distance is going to be 30 kilometers. And basically they're asking us to find the distance of the fire from each of the towers. So this is our Pine Knob over here, and this was the coal station. And our fire is over here on this side. Okay, so I'll give you guys just a little bit of time to think about this because there's some pre-calculations we'll have to do before we can get into the final stage. So what do you think we can do over here? And if it helps, we can label this as A. Let's do this guy as B and this guy as C, which means this will be side A, side B, and side C is actually what's given to us. So you're basically trying to find, if you look at the labels here, side B and A, right? The distance from the tower to the fire, or from the fire to the tower, however you look at it. Okay, Lucy, do you want to explain to me how you are coming up with that?
Well, so there's the two angles on the A side. There's
Mhm.
80 and 65 degrees. So I'm guessing you subtract 65 from 80.
Perfect, very nice. And that's exactly what I was looking for. So to find this angle over here, you're basically subtracting the two bearing angles that were given to us. So for angle A, I guess we'll do that here. Angle A, you're literally taking the 80 degrees and subtracting the 65-degree angle from it, which will give us 15 degrees. So this angle here is 15 degrees. Alrighty, perfect. What other information can we get? And I'm kind of going back and forth between the image itself. So maybe hopefully, you know, if my drawing doesn't make sense, this will be a little bit better. Do you think we can come up with angle B? We know part of it is 70 degrees. What can we do to find the other half, or, you know, whatever you want to call it? And that's where a little bit of geometry is going to be needed. Because remember, you've got the north and south lines here, right? From where we're calculating the bearings. So you've got this line here, which is going north and south, and you've got this line here going north and south, which we know are going to be parallel lines. So think about the relationship between parallel lines. You can use this as a, you know, line that is intersecting both of them. And we had actually done this in chapter 1 when we talked about the bearing angles, and, you know, we were looking at those ships and those other examples. I can't even remember. But we had talked a little bit about this geometry at that time. So what happens when you take a set of parallel lines and intersect it with another line with those angles? Alrighty. Very nice. Yeah, that's what I was looking for, guys. Let me get a new color over here. So this angle, which is being made between the north and south line and the line that's intersecting, this angle here will be the same as this angle over here. So that's that property that you are looking for. So since this angle here is 65, this angle here will also end up being 65 degrees. And like I said, since we already have the other side, you can go ahead and add both of them, and that will give you the total for that angle at the cold station tower. You know what, let's save this for a quick second here. Clear this out and go back. So very nice. Using that, we know this angle here is going to be 65 degrees. So that tells us angle B is going to be 70 plus 65, which comes out to what, 135? So what else can that then help us do now that you know angles A and B? Very nice, Savannah. All righty, so that will actually help us find angle C, which will come out to be what? And this is basically what we did. Yeah, Darren, very nice. We just did in those triangle that we solved earlier. Savannah, very good. So you will take 180 degrees, the total of the triangle, and then subtract 15 degrees and 135 degrees from it, which is what, 40, 50. So 150 is what you're subtracting. So yeah, that will leave you behind with 30 degrees. All right, wonderful job. So now we actually have the total angle is 135. So we've got all three angles, which will help us. We've got one side, because remember this side C here is 30 kilometers. So I will give you guys a minute or so. Go ahead and solve for both side A and side B. And of course, you're using law of sines to help you out with that. And then hold on to your answers. I want to give all of you a chance to calculate both sides A and B. And when I ask you to, you can then share your answer in chat. So don't share your answer just yet. And for now, we'll stick with 2 decimal places, though they didn't technically tell us how many decimals they wanted for this example, but we'll just stay, with the previous one and do 2 decimal places for now. And remember what I told you about larger angle will have the longer side across from it. So that should help you know if you're on the right track with your calculations and stuff or not. Okay, so get your answers ready. Don't send them again just yet. I want to make sure everybody's got a chance to finish the calculations and have the answers ready. And we'll go in alphabetical order. So type the answer A first and then answer B, which means since angle A was smaller than angle B, your first answer should be the smaller one and the second answer should be the larger one. All right, let's see those answers, guys. Okay, Lucy, Darren, let's see. Alrighty, while your answers are coming through. So to find side A, when we rewrite our formula, you would have A over side C sine C multiplied by sine of A. For side B, similar thing, you would have side C over sine C multiplied by sine of angle B. So this would be, let's see, 30 kilometers, sine of 30 degrees, and this would be sine of A was what, 15 degrees? This guy here would be same thing, 30 divided by sine of 30 degrees multiplied by sine of 135. So approximately, let's see, this guy came out to be 42.4264. And you guys were right on track here. We had 42.42. So Savannah, since you actually have a 6 in the third position, that would make the 2 go up to a 3. And then 4243, 4223. Darren, I'm not sure if that was just a typo. And then 4243. Alrighty, perfect. And yeah, very nice. This will be in kilometers because that was the distance, 30 kilometers between the two towers. And then for side A, the raw answer was 15.5291. So when you rounded this guy up, that came out to be 15.53. And in kilometers again, and that's what you guys had, 15.53. All righty, perfection. So again, two things you got to be careful about is, first of all, make sure your calculator is in the right mode. So since our angles are all in degrees here, make sure your calculator is in the degree mode. And then, with the given information, as you can see, we had to do a little bit of preliminary calculation before we were ready to, jump into law of sines and find our distances, from the fire to each of those towers. So this is the distance from the fire to Pine Knob. And this was the distance from the fire to the cold station. Okay, any questions on this example over here, guys? So again, just another example of where you were given 2 angles and 1 side. And you had to find 2 of the missing sides. And in that process, we actually ended up finding the missing angle also. So this is basically just that first case of using the law of sines where you're given 2 angles and 1 side, and you can see just different applications of how that goes. Now for the next one, this is the second case. So this is where we are given 2 sides and an angle opposite of them. Okay, so they're actually saying You saw that two angles and one side determine a unique triangle. However, if two sides and an opposite angle are given, then you can actually have three possible situations occur. You can actually have no such triangle that exists, so you wouldn't be able to solve it. You do end up with one triangle that would exist, or you can actually end up with two distinct triangles that would also be able to satisfy the condition. And because of this, that is why they call this the ambiguous case, because, you know, looking at just the sides and the angle, you wouldn't know if the triangle is going to exist, if you will have one triangle that satisfies the condition, or do you have two triangles that can satisfy those conditions. So here's the case in that. So they're saying consider a triangle in which you have sides A and B and angle A are given. So two sides, one angle is given. And they're actually giving you a little bit of a definition of how that height can be calculated. You know, if you had a triangle where you had to drop a perpendicular height to it, so that's going to be B times sine of A. So based on the angle that's given to you, if A is acute, then you can see in this situation, we can end up with these cases over here. If the given angle A is an obtuse angle larger than 90 degrees, then these would be the two cases that you would end up here. Then they're also telling you, is the side A smaller than that, perpendicular height in the middle? Is side A the same height as that vertical perpendicular height? Is side A greater than or equal to side B, which if they're equal, that would actually make it an isosceles triangle. And is side H smaller than side A and A is smaller than B? And then over here, you've got A being smaller than or equal to side B. And then the last one is A being greater than B. So each one of these are distinct cases. And, you know, depending on what you end up with, we can come up with answers or we cannot come up with answers for these, this case over here. So let's take a look at this example here. This one, as you can see, is talking about finding one triangle, a single solution. So we are given side A as 22 inches, side B is 12 inches, and angle A as 42 degrees. So you can, of course, see this is an acute angle. So if it is an acute angle, then you are looking at these first four cases over here. Okay, so, you know, just go ahead and draw your triangle, fill in the known information. So by using law of sines, since you are given two sides and only one angle, we don't have enough information to, you know, do 180 degrees minus angle B minus angle A or any of those calculations. So that's why you will see we have flipped over our law of sines. Sine B and sine A are on the top, sides A and B are on the bottom. So since we're trying to find angle B over here, you know, we get sine of B by itself, and then the side B gets multiplied on both sides. So then you end up multiplying side B with this fraction of sine A over side A. Plug in all the information that we know, which is given to us, and then based on that, you will be able to calculate your angle B. Now, you know, obviously, guys, they are going to use arc sine on this fraction over here to be able to find angle B. So, you know, inverse trigonometric functions. So once you have your angle B, we've got this one here. Now we can go ahead and do the 180 degrees minus the two angles to find angle C. So now we have the three angles, and we just have to find the missing side over here. So for the missing side, we can go back and invert our law of sines, put the side C on the top, you know, plug in the given information, and then you are able to calculate your given side C. So now we are able to get, you know, all three sides and all three angles of our triangle. So this was actually the situation where you had an acute angle and you got exactly one single solution. And, you know, that can be either one of these. That was our, because, you know, we didn't really calculate this vertical height over here, but you know, if A was greater than B, which is exactly what we had because A was greater than B, so that led us into this situation. Acute angle side A is larger than side B. We ended up getting one single solution. This next example over here is showing how you actually end up with no solution. So no triangle that would satisfy your conditions. So in this one, we are again given two sides and one of the angles opposite. This is obviously still an acute angle because it's smaller than 90 degrees. So now you can kind of see they have a partial triangle over here, but they are saying, okay, begin by making the sketch. Now, from this figure, it appears that no triangle is possible, and you can verify this by using the law of sine. So they went with sides A and B and angles A and B, you know, like you're trying to find angle for, you know, B. So using our formula, you know, we go ahead and plug this in, and you end up with sine of B equals 25 sine of 85 degrees divided by 15, and it's giving you approximately 1.6603, which is a number larger than, you know, slightly greater than 1, I guess. But here's what's happening. You know, they're saying this contradicts the fact that absolute value of sine of B has to be less than or equal to 1, because we are basically saying no triangle can be formed where you have a side of 15 feet and the other one is a side of 25 feet and your angle A is 85. And this is where you kind of want to go back and look at this condition over here. When your A value is going to be smaller than your H value, you do not end up with a triangle. And you can see for the H, you just have to do B multiplied by sine of A. Okay, so let's see, what will that end up giving us? B is going to be 25. Sine of A will be sine of 85 degrees. And what will that end up giving us? 25 times sine of 85. Come on. It's coming out to be approximately 24.904. And they're telling you if A is going to be smaller than your H, and our A value was 15 feet. So if your A value is going to be smaller than your H value, you are not going to have a triangle, because think about this just in terms of, you know, geometric sense. Let's clear all of this out here. So we are basically saying this height here, going from the tip of the triangle to the base of the triangle, has to be, you know, 24.9. So just shy of 25 feet. So if this is where the triangle is headed, you know, 15 feet is not enough to make it to the base of the triangle, right? I mean, that distance is way too short that it will reach all the way down, you know, just the way it is given. So there is no way that this part would connect to the base of the triangle. So that's kind of what's happening over here, is that side A is not long enough for this triangle to actually exist, because, you know, what you would have to do is, instead of keeping your base here, you would have to change this angle. And if you change that angle, which means this guy cannot be 85 degrees then. This has to be a much smaller angle. So that's kind of what's happening over here, is your measurements just do not add up to a possibility that you can have a triangle which will, you know, match these dimensions. Does that kind of make sense why we were not able to solve this? Yeah, okay. And then, you know, of course, you have the case where you can have two solutions for the given condition. So this one over here, I think my battery might be dying in my pen over here. So here again, you have A as a side A is 12 meters, side B is 31 meters, and then, we're still looking at an acute angle. So here, sides A and B, coming back over here, you can see they're telling us here that your side A has to be smaller than side B, and both of them, would be larger than side H. So again, if you went back and calculated H, if that side ends up being smaller than both A and B, then you're going to end up with two triangles. So again, your H is B times sine of A. So if you wanted to verify that very quickly, that means we would end up doing H is side B, which is 14 feet, times sine of 60 degrees. So 14 times sine of 60 ends up giving us approximately 12.124. Keeps going. Okay, so the H had to be smaller than A and smaller than B, which H is definitely not. Oh, sorry, I was looking at the wrong one. Yeah, but still your A is 12 meters and this is 12.124. Oh, I used the wrong angle. Sorry, I was looking at this guy here. So that should actually be not these numbers. Okay, so this is actually B is 31 meters and angle A is 20.50. Okay, 31 times sine of 20.5. Yeah, so you are ending up with 10.856. So that will round up to 10.86 meters. Okay, so we do meet the conditions. Then your side H is smaller than side A and side A is smaller than side B. So we're definitely meeting those conditions for two cases of triangles over here. So same thing, you go ahead and find what your angle B is. Once we find angle B, we can come up with angle C, but this is where you will actually run into this situation over here. So you'll see we go ahead and plug in our numbers and your sine of B comes out to be 0.9047. So because that number was small enough, you can actually come up with two angles that would be between 0 degrees and 180 degrees. That would be approximately equal to sine of, angle B, giving you the sine 0.9047. So that would actually come out to be 64.78. And when you do 180 minus 64.78, you will end up with 115.22. So anytime, this value is small enough that you can subtract it from 180 and get another angle, you will end up with two cases. So now this is going to be, that's why you have B sub 1 and B sub 2, because you get two cases, two different angle measurements. And that's where those two triangles are coming from. So based on the first measurement of angle B, which is 64.78, you can of course see when I use B1 as 64.78, putting that into our measurement for angle C, you will end up with angle C being 94.72. Once you get that, we can go ahead and find side C, which comes out to be 34.15 meters. However, if we go with the second measurement for angle B, well, that means our angle C is going to come out to be a slightly different angle. And then based on that, your side C will come out to be a little bit different also. So you can see that's where we are ending up with the first triangle over here and the second triangle over here. And you can see what those two triangles end up looking like. So they're both satisfying our conditions, but just because of that fact, that angle B can actually have an acute or an obtuse measurement, you will end up with two different triangles. So that's kind of where this idea is coming in from. So let's work out a couple of our own examples here. Let's see, I believe. Okay, right here. So they're saying use the law of sines to solve the triangle. If two solutions exist, find both, and we are still rounding our answers to 2 decimal places. Okay, let's do number 23 over here. Okay, so we are given angle A, side A, and side B. So we can start by finding sine B again. So again, we're actually doing sine of A over A, sine of B over B, sine of C over C. So this is the law of sines we're using. So since sine of B is on the top, of course, we will have sine of A divided by A, and then you would be multiplying this with side B. So just rearranging our formula again. So this will give us sine of A would be sine of 110 degrees. Side A is given to us as 125. Side B is given to us as 100. So sine of B will come out to be, what does that end up giving us just for sine of B when you simplify that right-hand side?
Is it 0.75?
Yeah, it's going to be a fairly smaller number. And so what you want to do, guys, because remember, this is not our final answer. This is just getting us to our final answer. I would suggest do not round this answer, because if you start rounding it here, your angle measurement will be less accurate. So 0.75, 175, 4097. That's kind of what I'm seeing on my calculator here. So now to get angle B by itself, of course, we would end up doing then arc sine or sine inverse on both sides. And of course, since you're using your calculator for this, it's easier if you, again, don't round your answers. Once you get to angle B, then you can round it to 2 decimal places. But for the sine B, don't round that 0.75, 175, 4097. So what do we end up getting for angle B once we do this arc sine?
48.74.
Yeah, and that looks like a good answer. So 48.7425, and it keeps going, but since we're only rounding it to 2 decimal places, this will be 48.74 degrees. Alrighty, we have our angle B. So now that we actually have angle A and angle B, we can now go in and find angle C. So what will that come out to be, guys? And since you have 2 decimal places in angle B, that will automatically give you 2 decimal places in angle C. So what do you have for angle C?
I got 21.26.
21.26. Okay, did anybody else have that answer? Yeah, Darren, Andrew, okay. Alrighty, perfection. So again, subtract 110 for angle A, 48.74 for angle B, and that will give you 21.26 degrees for angle C. Okay, so we have all 3 angles now. We already had all the 2 sides, so that means we just need to calculate side C. And for side C, we will of course have to invert our formula. So you will be doing side C sine C. And since we were given angle and side A, that's what I'm going to use to calculate this, because again, we don't want to use any rounded answers, if we can avoid that. So that means side C will be A divided by sine of A multiplied by sine of C. So what is that? 125 over 110 sine of 110. And you're multiplying it with sine of 21.26 degrees. So what are we looking at for side C? And this answer, again, you will be rounding it to 2 decimal places. So let me see in chat what you guys came up with. Okay, Savannah, Andrew. Let's see, all right, perfect, guys. So 48.2339, and it keeps going. So rounding it to 2 decimal places will be 48.23. And again, they didn't give us, if this is inches, meters, or what, so no unit. But this is going to be our side C. So, obviously, as you can see, this was an example of one single triangle. And again, just to show you, oops, those conditions. This is if your side A is greater than your side B. And of course, our side A was 125, side B was 100. So this was side A greater than side B. So it's actually the third case that you are looking at over here. So that's the case that we looked at in this calculation. Okay, so that was number 23. Let's see if we can find something. Let's do 27. And I might actually have to move this guy over to our notebook. Okay, so we are given angle A as 58 degrees, side A as 11.4, again, no measurement unit over here, and side B as 12.8. Okay, so when we look at the case over here, you can see side A is smaller than side B. And then, we can go ahead and calculate H to see if it's going to be a number smaller than both A and B. So to calculate H, it's B times sine of A. So that's 12.8 times sine of 58 degrees. So what do we get for this guy?
$10.85.
Sorry, say that again.
Right, I think 10.85.
10.85. 10.17, okay. What did I do then? 12.8 times sine of 58 degrees. Ah, didn't type in my whole thing, sorry. 10.86. Well, so yeah, as you can see, we are able to verify, that should be approximately, that this is going to be smaller. So H is smaller than A is smaller than B, which means we will end up with two triangles in this case. Alrighty, so as usual, start by taking your sine B, and that will be sine of A divided by side A and then multiplied with side B. Let's see, that will be sine of 58 degrees over 11.4 multiplied by 12.8. And let's see, what will this end up giving us? Sine of 58 divided by 11.4 times 12.8. And again, remember, this will give you sine of B, and then you will have to do, again, the arc sine or sine inverse to find what angle B is going to end up becoming. So this will end up giving us 0.952194354. So make sure you are not rounding this answer over here. And then, you know, of course, then calculate your B by using the sine inverse. And then what are we looking at for this one? So when you do sine inverse of 0.952194354, what angle measurement do you get? Yeah, Lucy, very good. So rounding it to 2 decimal places. Andrew, very nice, perfect. 72.2121, and it keeps going, but we'll round it to 2 decimal places, so 72.21. So we'll actually call this B sub 1 like they did in our handout, because this is going to be one case, because this angle is small enough that we can actually get 180 degrees minus 72.21 degrees, and we will still be able to get a B2 angle, which will of course end up giving us So again, this is where the two cases arise from, right? Because the angle was small enough that we were able to do a second angle from that. Okay, so case 1, case 2, this is where you're going to use the B1 as 72.21 degrees. Here we will use B2 as 107.79. So obviously you can see we have 2 of the angles now. We need to find angle C, and you already have 2 of the sides, so you need to find side C. So let's start out with angle C over here, which will come out to be 180 degrees minus A was 58 degrees. And then from that, subtract 72.21 on the case 2 side. Pretty much the same thing. Angle B will change. So minus 58 minus 107.79. So what are our 2 angle C's looking like over here? What's your first angle C and your second angle C here, guys?
For the second, I got 14.21.
14.21, okay. And for the first angle, folks. Yeah, I knew I was doing that wrong. $49.79, all righty. So I actually had sine A on the top, but that is when you're trying to find the angle. When you're trying to find the sides, side A has to be on the top and sine A on the bottom. And then sine C over here. All right, let's see your two sides for C. And again, since your angle measurement changes on both sides, side C is also going to be two different values. So for case 1, what is your side C? And case 2, what is your side C?
For the first triangle, I got 10.26.
Okay. And actually, when you round that answer, it will be 10.27, and they didn't give us measurements, did they? No. Okay, and then guys, what did you get for the case 2? Now remember that angle is smaller, which means this number also has to be smaller than 10.27. Okay, 10.26, Savannah, and 3.30. Okay, so just be careful with that rounding because you had 265. It will actually go up to 10.27. And then you said 3.30. Yeah, and that should be a fairly smaller number because your angle is so small. So 3 point, and the raw answer comes out to be 3.29985. So when you're rounding it to 2 decimal places, this 9, of course, will make this 9 go up. So 29 will actually end up becoming 30. So 3.30 looks good for this guy. Questions on this one here, guys? So what I would suggest is when you're working through these homeworks, and especially in the instructions where they say if you have 2 cases, show both of them, try and do these little calculations over here so that you can kind of see, are you going to have no triangles that would satisfy that? Do you have 1 triangle or 2 triangles to do that? So we did the case for 1 triangle and 2 triangle, but as you kind of saw with this example here, what would end up happening if you didn't have any triangles that would satisfy. So you will see examples like this in your homework for sure. And then the last part of this section is actually kind of where we get into how you can calculate the area of an oblique triangle. So we'll talk a little bit about that next time, and then we'll get into section 3.2 on how we can solve the remaining 2 cases based on law of cosines. So that's kind of where we are at. Hopefully you have enough information that you should be able to start working on section 3.1 homework. And if I can find an example for next class where I can show you what happens where you have no cases at all, I'll try to find one in our textbook. So maybe we can work on one of them and then get into the area of the obtuse triangle. So that's where we are, guys. So have a wonderful day, everyone. Be careful, stay safe, and I will see you on Monday. Take care, guys.
Thank you.
Have a good weekend. Bye.